agent. There's a method in it named update. And here's what it does. It calculates 20 values. Value number 0 is your x position divided by 600 minus 0.5. Value number 1 is your y position divided by 600 minus 0.5. Value number 2 is the arctangent of your position, your y and your x divided by 4. What's that doing? This is the polar representation of your location on the screen. This is the distance you are from the origin, so the distance of your ball from the center. You see that? Let's look at this one. This is how fast you're moving in the x direction, how fast you're moving in the y direction, the angular direction in which you're moving, the speed at which you're moving. This is your opponent's position, how fast your opponent is moving, where you are relative to your opponent. Basically, it's just all the data you would ever want. Do you see that? Okay. So we're going to use a neural network to take all the data that you would ever want to know about the game, what's going on, what the current state is, and based on that, we're going to decide what direction to move and how fast to move in that direction. Basically, if you get the right stuff in this box, the ball behaves intelligently. Can you see that? All we need is to get the right stuff in the box. Well, what this box is a neural network, and a neural network is a big, nasty, hairy math equation that has a whole bunch of coefficients, a bunch of parameters. We call them weights. And if we get those weights right, the balls will start to behave intelligently. So your goal in this assignment is to get the weights inside the box to be pretty reasonable. Okay. Now, as I've looked, let's look at game. This is where it all starts. The game class has a method here named main. Now main here, you'll see it makes a new neural agent with Bob. Bob is this massive vector of numbers, right? I think I told you before that I obtained these big vector of numbers by implementing a genetic algorithm, and I evolved for 50,000 generations. So if you want to beat mine, you just need to implement a genetic algorithm that's at least as good as my implementation and run it for 50,001 generations, or maybe 2 until it gets better. And presumably the vector that emerges from yours is going to be a little bit better than this one, and you'll make a vector and hard code it in here, and then you'll come down here and battle your agent. Instead of Randy, you'll use your name or something like that, and your sumo ball will beat Bob. Okay? Does that make sense? Good enough? You get the high-level picture of that? Okay. Well, right here I made Randy. Randy is a new double of 291 values. The reason there's 291 is that's the number of weights in this particular neural network. You shouldn't need to mess with it. You don't need to understand neural networks. You don't need to understand where those weights are going. All you need to know is you make an array of 291 double precision floating point values. You pass it to the constructor of neural agent. That will create a neural network that controls your sumo ball and will play it in the game. And if you call do battle, it will do battle. And if your numbers stink, Bob will beat you. Okay? So you do need to know enough to create an agent and do battle. That's easy, just copy that code. And you need to implement a genetic algorithm to evolve these numbers. Okay, so when we come to your matrix, we know that n needs to be 291. What should m be? I'm going to say use your own judgment, and you pick. What do you think will happen if we say M is 10?
You probably won't get that good of results.
Probably. However, honestly, I wouldn't be surprised if that works really well. Here's why. Let's suppose you say M is equal to 1,000. Can you see that this is going to take 100 times longer on average for each member of the population to change by about the same amount? That is, if your mutation rate randomly picks 1 each time. In genetic algorithms, if you make the size of the population really big, why did I use M here? They always use N for that. That one's M. I'm sorry, I messed up. N is always the size of the population. Anyway, that's irrelevant. If your population is, say, twice as big, it's going to take probably twice as long. Now, that's kind of the way it tends to be, but in reality, that's not totally true because you have to have some amount of population to support each other because you need to be able to explore. So if your population is really big, you're kind of exploring the space of possible genomes, right? Now imagine that you had M insanely big. How many iterations of evolution would it take before you discovered a really, really great genome? A really great chromosome?
Maybe only once.
Yeah, I'm going to claim maybe 0, because immediately someone in your population is just going to get lucky, because that's a darn big population. So arguably, a really big population is better, except you're only going to be able to do 0 iterations of evolutionary optimization before your computer is swamped, because that's a lot of members of the population. Or rather, it'll take that long before everybody has the chance to update even once. So it's going to be slow. Conversely, if you have a very small population, well, now you're sampling the space very, very poorly, but the same 10 are going to get updated over and over and over, and a lot of churn will happen, and maybe they'll find a better chromosome. So what's the right answer? I don't know. 10's about the bottom limit. Don't go less than 10, it won't work. 100's probably good. 1,000's getting kind of big. 10,000, this would be reasonable if you were going to let it run for days, and if you have a supercomputer or things like that. This is probably a pretty typical size population. Once you're getting up to 100,000, frankly, you're wasting your time. You're mutating chromosomes that are never going to evolve, so you're just, unless you have ridiculous amounts of computing time, this is getting too big. Okay? So you have some intuition for what parameters to use there? Okay. Now, so how do you implement mutation? You pick a random number, change it. Because because our chromosomes are not Gattaca, they're not guanine, adenosine, cytosine, whatever the amino acids are, they're actually continuous valued numbers. Now how do you mutate it? Well, I'm going to say, draw a random number from a Gaussian distribution and add it to your number. Okay, so how do you draw a random number from a Gaussian distribution? The java.random class has a nice method called nextGaussian. It will return a Gaussian number for you. It returns a Gaussian number from a standard Gaussian distribution, which means it has a deviation of 1. That's not necessarily the right deviation. But for now, we'll just say, just draw a number from that, add it to your number, and there, you mutated it. Okay? Now, for selecting the most fit chromosomes, you can use the controller rank agents method. Okay. I provided a really nice feature for you here. In my controller class, there's one function you need to know about. You don't need to know how it works, but it wouldn't hurt. This is called rank agents. Now, what you do in rank agents is you pass in an array list of agents, and what it does is it performs a pairwise competition between every two agents. And then it counts up how many times each one of them wins, and it returns to you this array list, or this array of indexes of the winners. So element 0 in this array is the index of the agent that performed the best in all of the tournaments. Element 1 is the index of the array of the agent that performed the second best in all of the tournaments, and so on and so
And it
forth.
just battles against the ones that you pass in. They just battle each other.
Yep. So if you pass in 10 agents to this list, then it will perform, let's do an easier number. Let's suppose you pass in 3 agents to this list. Agent A will battle against Agent B. Agent A will battle against Agent C. Agent B will battle against Agent C. Actually, it does it both ways. So it's going to be 3 times 3, there will be 9. If there's 10, it'll be 100 battles. It does every battle with each agent playing red and then each agent playing blue, and counts up the total number of wins, sorts them, returns it. If you're to actually look at the code, you'll see that's what it does. Here it calls do battle, no GUI. No GUI means don't show it to me, I don't want to see it. We sort the agents by the number of wins, return the list. Okay. Essentially, I've done all the work for you. That's the hard part. The hard part is setting them all up and running these tournaments and seeing which one's the best, so that should be really easy for you. If you want to, you can use do tournament. This actually does a single tournament, so you, oh no, this does all of them. Here's a, what is it? It's do battle. You can call do battle directly yourself if you just want to do a battle between 2 agents and see which one wins. Okay. So that's what you need to rank the agents. Okay, now what are you going to do after you call controller rank agents? In your code, you've got this array list of chromosomes. You've ranked them, you figured out which ones are the best, which ones are the worst, then what?
Kill the worst.
Yeah, so maybe pick the worst 10% and say goodbye. Delete them or 0 them out or just leave them there and then tell the others to have babies and stomp the babies over their slots. However you want to do it, but somehow the worst ones are going to die, the best ones are going to live. Okay? Then, for replenishing the population, please implement crossover. Okay, let me talk about what crossover is. Okay, here comes the mom. The mom has GHACHEAZ, and the dad is TACCAGGAGGA. Okay? Mom and the dad have sex. Then the baby is basically going to get some portion of the mom's chromosomes plus some portion of the dad's chromosomes. I have now done crossover. Any questions?
Should it always be 50-50?
Ah, that's a good question. So, how to implement crossover? Essentially, you're going to use part of one and part of another and produce the result, and as long as you do that, you could call that crossover. So the crossover is a pretty vague system. Obviously what we're doing here is we're being inspired by the genetic recombination that occurs in sexual reproduction. So the idea is you have 46 chromosomes, you get 23 from the one parent, 23 from the other parent, and the mixture of those 23 chromosomes produces all kinds of combinations, and so they all have siblings. Now, The most common type of crossover implemented in genetic algorithms is called single point crossover. The way it works is you pick a random point. So pick a random number between 1 and the end of the number of elements in the chromosome. And wherever that point is, we call this the crossover point. So we take all of the father before that point and all of the mother after that point, or vice versa. And that makes the child. So the idea of single point crossover is there's a single point where you cross over. And then you've done it.
So we're doing this to doubles? Or
Yeah. Now, in this particular case, you've got this array of 241 double precision floating point values. So basically, pick a random number from 0 to 240, and whatever number you pick, all the ones before that come from one parent, all the number after that come from another parent. This is single point crossover. Guess what other kinds of crossover there are? There's one called double point crossover, where you pick 2 points, and then you go to the point, and then you switch to the other parent, and then you switch back to this parent. And then some genius came up with triple point crossover. Obviously, we can go to the extreme. Here's the extreme. At every single element, we flip a coin, and if it's heads, we pick from the mom. If it's tails, we pick from the dad. So somewhere between single point crossover and n point crossover is probably one that works pretty well. If you want, you could roll dice to figure out what number of crossover points to use, and then you could implement that number of crossover points. And then you've got all kinds of weird genetic recombination things going on. And what's fun about genetic algorithms is the weirder you get, the more likely it is that you're going to explore the space well, and eventually you're probably going to find something that's good. Does that make sense? So it doesn't have to be biologically inspired. It's actually okay to go weird, go a little beyond whatever biology is doing, and come up with your own operations. That tends to actually improve genetic algorithms rather than harm them. As long as you have the major components of somehow promote diversity, somehow kill off the less fit ones. Yeah?
So I'm guessing this is just bonus on averaging them and then taking that probably wouldn't be good then, since we're using them.
That's another way to do recombination. If you were to average them, however, imagine that you were always averaging them. You see how the population would kind of shrink to the same point? If you take a bunch of points and you keep averaging, you're always going to be pulled inward. There's this sort of inward pulling force. So let's talk about that. Let's suppose I plot these chromosomes. So I've plotted some chromosomes. Now, because this is a two-dimensional whiteboard, you can only assume there are two numbers in this chromosome. They're very short chromosomes for the moment. But I picked 2 parents at random. There we go. I'm going to average them. Bing, there's the child. That's what will happen if you do that. What will happen if you do crossover?
Just be a random spot on the
Do you see that interpolation gets you here? Crossover kind of gets you there, or it gets you there, right? Because you're taking one of the values from one parent and one of the values from the other parent. It kind of reaches the corners of whatever the parents do. Except we're really in hyperdimensional space, so there's a lot more corners, and it sort of does this type of a thing. Which operation makes more sense? They both make sense in different situations. Interestingly, the crossover seems to be very, very effective. Interpolation seems to not really add very much. So in this assignment, I'm asking you to implement some type of crossover, not interpolation. However, I'm not saying don't do interpolation. If you want to add that as a possible operation too, that's better than just doing crossover. The more things you do, the cooler your algorithm is in genetic algorithms. Yeah.
So why is crossover, or how is crossover different than just randomly picking a point?
Well, if you have these 2 parents, there's no way the child will be out here, because no parent has a value in this dimension that's way out there. So crossover definitely won't do that. Do you agree? Now, why is crossover better than doing that?
Because we're already assuming the parents have traits that we want.
Yeah, so here's the intuition. We assume some amount of evolution has already occurred. So the population has kind of drifted toward goodness. And if that has happened, then crossover is likely to produce a child that's also basically not retarded. Whereas if you pick random chromosomes, chances are you're not going to get a good child. Now, if you're early in the evolutionary process, crossover is going to do just as badly as picking random. So random actually works really well early on, but the more evolved your population gets, the less useful random seems to be. Yeah.
So at the beginning, our population is purely random?
Yes, probably.
Okay.
I put probably in there because, in fact, it works if your population is initially random. It works if your population is initially somehow intelligent. And if your initial population is intelligent, you might have saved yourself a bunch of effort. So on that note,
How would you
Since-
make an initially intelligent population?
Take Bob
since your entire goal
Oh,
is to beat Bob, do you think it might be a good idea to have Bob be in your population to begin with?
Son of Bob.
Yes, son of Bob. Right. If Bob has enough children, you're just going to beat him. Now, partly that makes the assignment kind of stupid because if it only takes you a few generations to find one better than Bob, what was the point? So I'm going to stick with the instructions say you just have to beat Bob. So if you beat Bob, you get full credit. But just for the sake of learning a little bit, see if you can beat Bob without including Bob. Just because you're awesome. And if you don't, I'm not going to even look. But it would be cooler not to even include Bob in the population, just because then you can prove that you coded yours up at least as well as I coded mine up.
What if about 7% of our random population beats Bob anyway? Like our initial population?
If that happens, I'll be darn surprised.
Oh, it did.
Oh, wow. Well, maybe it's a stupid assignment, but we're going to pretend it's awesome anyway and move forward. So you're saying you pick random numbers and they beat Bob.
Yeah, I just used the next Gaussian and generated like 300 and about 7%. Yeah.
Dang.
A few more
I
100,000.
kind of figured Bob would do pretty well because I evolved him for a long time. And then as a human, I battled against him, and I had a hard time beating him. And I even battled Bob against Bob, and he survived for a while. So I'm really surprised that random numbers beat Bob. That's too bad. Okay, I guess this is one of those assignments where the wimpy people that aren't interested in learning are just going to not get a darn thing out of it. I feel bad about that. I just don't know how to enforce it any better. So we're going to still do it. And you're still going to code up a full genetic algorithm, even knowing you could probably just draw random numbers and beat him pretty efficiently. Darn, I wish I didn't know that. And I wish you didn't know that. Yeah, well, that's what we're going to do. Let me show you what I did to the last year's class. Okay, so assignment 2. I had them do this problem. So do you remember this problem where we're searching for the optimal path to get from here to there? We used a genetic algorithm to evolve a path. And each chromosome in the path represented a direction and, was it a step size? Yeah, I think we had a direction and a step size. And so you can imagine a path being a sequence of chromosomes, right? And so we evolved until the path got from here down to there. And we generated some really interesting animations of these paths initially starting out dumb and so eventually evolving until they pointed down there and then evolving until they kind of followed the nicer paths and things like that. It's a good example because it is easy to visualize on two-dimensional plane. It's a bad example because genetic algorithms stink in 2 dimensions. They're really well designed for big, high-dimensional problems. And That's why I improved them by going to assignment 4, which I thought there'd be no way to beat just by picking random numbers. Okay. So, I forgot where I was. We did crossover. Oh, I wanted to finish on crossover. Okay. One other operation you can do. Suppose you did a weighted interpolation. Suppose you pick a random weight, you give 80% of the weight to the mother and 20% of the weight to the father. Where's the child going to end up? Right there, right? Well, if you pick a random weight, it'll be somewhere, anywhere along here. What if you pick a weighting that instead of between 0 and 1, you pick a weighting between, say, 0 and 2, or 0 and 3? See what'll happen? That'll basically make the child go like this. The child will be so much like its mother that it's like its mother minus some of the father. The nice thing about this is whereas interpolation has the tendency to pull the points together over time, if you pick a random value between 0 and 2, it's just as likely to throw the child out there as it is to pull the child in. And so this is extrapolation, whereas this is interpolation. And if you're going to do interpolation, you might as well just do extrapolation by randomly picking your weights. And that makes a really nice operation for genetic algorithms. So this is not one you actually need to code up. You do have to do crossover for this assignment. But if you want to do crossover and interpolation and extrapolation, then you've got a really nice way of promoting diversity in your population while replenishing the missing members of your population. Okay. By the way, if you want to add as a one possible operation, start a new random member in your population, apparently that's going to work really well in this assignment. And it's not a bad thing to do in general. Suppose you add an operation like this. Is there any chance that could just totally screw up your genetic algorithm? Well, there's always a chance, but it's a slim chance because presumably when we do a tournament, the new guy's just going to always die. Unless that new guy happens to be brilliantly effective at staying alive, in which case, well, hey, it's really good. And then it's going to survive and have offspring, and pretty soon the population will kind of migrate over to the really good spot. Does that make sense? So it's all about wherever the population is surviving, that's where they're going to keep surviving. Where they're dying, that's where they're going to die off. So eventually the population is going to go where it's effective. Okay. Okay, you may use a fixed size population. Some other metaparameters will also be required, such as the mutation rate and the average deviation of each mutation. Okay, how familiar are you guys with the Gaussian distribution? Not at all? Okay. Let's look at this. Normal distribution. Let's look at the Wikipedia page. Here's a picture of the probability density function of the normal distribution. Excuse me. The normal distribution is often called the bell curve because it looks like a bell. Does anybody think that looks like a bell? I don't think it looks like a bell, but it's called a bell curve. The idea is it's most likely you'll draw a value around here, kind of unlikely you'll draw a value here, just about impossible you'll draw a value out here. But by just about, I mean not impossible, just almost impossible. So Gaussian values usually fall around here somewhere.